Thanks for having me in this AMLD EPFL talk. Hi, my name is Saehong Park. I'm a postdoctoral researcher at UC Berkeley. Today, I'm going to talk about the deep reinforcement learning for battery fast charging. So as you may know, the batteries are everywhere. You can find any lithium-ion batteries in your smartphone or in your electric vehicles. So as you can see, lithium-ion battery increases its market share for electric vehicle and urban transportation these days. As you can see in the below figures, the battery costs are dropped huge, while the battery demand is increasing exponentially. And it reaches almost the goal of using electric vehicle. The cost is around $150 per kilowatt hour in 2019. So as more batteries are dispatched in this our real world, the optimal battery fast charging is much desired. And that is also so-called advanced battery management system. So what is advanced battery management system? This is basically we rely on the more detailed mathematical models and guarantees its maximized performance and safety. So in this talk, I will introduce what is the battery charging problem in the context of optimal control problem and reinforcement learning. So the ideal usage of battery, as I said before, we want to charge faster and use longer. That is the ideal battery strategy. And to do that, as an indicator battery fast charging, we used the level of state of charge, which is the amount of lithium concentration in the anode side. And as an indicator for lifespan or state of health, we set as the violation of state constraint. So here, let me show you a video about what is the conventional charging protocols in battery fast charging. So here, we use a simulator and charging the battery. So red profile is burst profile. So in the top figure, you can see that the total the capacity that charge the battery. So they are basically the same. And you can see the trajectory of the input profile as well as the output voltage profile. And you see that the state of charge is increasing as battery is charged. But in the internal battery states, such as side reaction or potential, it's different with different charging strategies. And you can see that like constant charging profile, it's less violated than burst profile. And that affects the battery lifespan when you use the battery in the amount of time. So this is the motivation. How do we design a battery fast charging protocol while not violating health-related constraints? So in the literature, we can view as a model-based control strategies, such as model predictive control, or combining estimator and controller, or using reference governor. In this model-based approach, we still have model uncertainty. And it's also depending on the model, it can be formulated as a large-scale optimization, so computationally intense. And lastly, battery itself, it changes over time, so-called battery degradation. So we need to re-update it or re-identify the models in order to not violating or in order to mimic the battery system. On the other side, people have been using a lot, and especially experimentally, using model-free charging strategy, such as CCCB protocol. So in the CCCB protocol, which is commonly used in the industry, that is set the constant current level, and once it reaches to the maximum voltage, and keep the maximum voltage while decreasing the amount of input current. Also, PID control is commonly used as a tuning approach. So in this model-free charging strategy, the challenges are by following. First, we have lack of optimality. Those profiles can be obtained by heuristics. And second, it also lack of adaptability. So since it's manually fitted to the current model, once the parameter changes, we will see that it immediately violates the constraints. So this motivates us to use reinforcement learning, especially actor creating method for designing charging strategy. And in this talk, you can see how this learning-based control can be comparable to the existing control strategies, such as a model-based charging strategy and the model-free charging strategy. Okay, so let's pick up one of the batteries. So here we pick the NCA 18650, which is commonly used today's electric vehicles. And the modeling side, we are interested in the electrochemical models because it describes internal behaviors of batteries. So inside the battery, we have in the mathematical modeling is also very challenging. We have a couple of partial differential equations, ordinary differential equation, as well as algebraic equations. So it is notoriously difficult to solve this mathematical model numerically and come up with the optimal control problems. So as I said before, we use state of charge as the level of concentration in the anode side. And for state of health constraint, we used side reaction potential as a lithium plating constraint here, based on this electrochemical model. Okay, so suppose we have 1 to 15 this type of model, discretized by numerical method, and then we can design an optimal control problem. So the goal of fast charging is we want to minimize the final time, TF, by designing input current, IT. And we have input constraints as well as state constraints starting from initial conditions. So how to solve this optimal control problem is also open topic or is well established in the solving optimal control methods. There are three main strategies to solve these optimal control problems, such as dynamic programming, indirect method, and direct method. So there are many numerical schemes to solve this optimal control problem, also guarantees its optimality in the model-based control. Especially the reinforcement learning is overlaps in the context of dynamic programming. So in the next slide, I will briefly discuss how do we solve it, this optimal control problem and using in the data-driven approach. So here we use the algorithm called deep deterministic policy gradient, which is one type of actor creating network. So what is the actor creating network in the learning approach? It is actor placed as a controller and critic placed as a value function estimate. And DDPG is proposed by researcher Lily Crabb in 2016. And the value function estimate critic part is estimate the value function from generating or data samples from the policy or actor. And once the value function is estimating from data, and it updates its control policy to maximize its reward. So you can find more details about reinforcement learning algorithm, and there are a number of reinforcement learning algorithms, especially for continuous action space. So using this DDPG algorithm, here is the simulation result. How do we obtain this fast charging protocol using deep reinforcement learning approach? So the top figure, you can see that the score of learning approach. And then in the middle figure, you can see that the profile that learning agent can come up with, as well as the voltage profile, output profile. In the below figures, you can see that whether it is violated its constraint or not. So in the beginning, it starts with a very large amount of time for charging, as well as violate constraint. But as you can see, after 1,000 episodes, it doesn't violate constraint and writing the constraints while minimizing its time steps. So that is how we can see or how we can understand to find out the optimal control strategy for battery fast charging. So after this training, we also checked whether it is valid or valid constraints or not. And for battery fast charging, the temperature is another key impact factor. So we consider different ambient temperature cases and see whether it violates constraints or not. So for state-based policy, assume that we are able to measure internal states. And the left top figure shows that the cumulative return of the control policy, and you can see that it's after 1,000 iteration is almost close to the maximized reward, while the temperature violation and the lithium plating violation, here we compute as a violation score. So plus the positive sign means that it violates constraint, and the negative sign indicates that it doesn't violate the constraint. And you can see that the ADA-SR or side reaction constraints is the main one in the for the battery fast charging case. And lastly, you can see that battery charging time decreases while we come up with the battery fast charging strategies. Also, we compare with the output feedback controllers concept. So here, suppose we are not able to measure internal states, only measure voltage and the temperature, and how do we come up with the fast charging strategy here? And as similar to the state-based policy, we are able to obtain the fast charging protocol that charge the battery in 45 minutes. So as a validation, we compared states-based policy case. We use the baseline as a modified reference governor, which is similar to the model predicted control, just looking at 2 or 3 times ahead and check the state violation and derive the control strategies. And in output feedback or output-based policy, we compared our approach with the PID control for the CC-CT-CB charging profile case here. And we say we can find that the reinforced learning or learning-based policy can be comparable with the existing approach. And one benefit or one critical aspect of using reinforced learning is it has its own capability of adaptability. So as I said before, batteries are changing over time. And how do we come up with this or adjusting controller side? And if we are keep continuing the learning or training our strategy, and it is able to change their control policy, not following constraint. So, and this figure we compared as the parameter changes in every 100 cycles, and check that if it's not updating, then our pre-trained model violates constraints. So we see the huge violation in the reward. But reinforced learning itself, it has its own adaptive controller strategies. So we also validated with the existing approaches. And as you can see in the below figure, it violates its constraint, while the adaptive reinforced learning controller is not violating its straight constraint over the charging profile. And we also check the charging time and check what are the benefits of using reinforced learning control. That is, one is adaptability, and second one is we can reduce the complexity. So in conclusion, here we use reinforced learning as a general toolbox for solving optimal control problem, and it can be viewed as a heuristic dynamic programming, also approximate dynamic programming approach. And interestingly, RL can be played as both state-based state feedback or output feedback controller for battery fast charging. And lastly, one key aspect of using reinforced learning is it has its own it plays as a direct adaptive controller. So it tunes its control policy as it violates the constraints. Thank you for listening, and I'm happy to answer your questions.
Thank you very much for this very interesting talk. Questions will appear, I'm pretty sure. The first one I'll claim for me, and this is the following. Have you already tried your approach on a physical device that is a real battery in the lab? Or is this all the charts you showed based on simulations?
Mm-hmm. Yes, correct. So we first used the real battery. So the electrochemical model inside, we adapted all the parameters. So we checked that it is same as the experimental measurement. But for training side, we rely on the simulation toolbox. So our point is, once we have perfect modeling from the manufacturer. So this work is cooperated with the LG Chem battery manufacturers. So they provided exact electrochemical parameter sets, and we training in the simulation. And we come up with this battery charging protocol side, and we compare with the existing approach. So the answer is yes, we combine the model itself is close to the real batteries, but for come up with the this optimal charging profile, we rely on the simulation tools.
Okay, clear. Thanks for the answer. Another maybe interesting question can be this one. We saw in the previous talks that a lot of effort is going into integrating batteries into larger pictures, like a whole neighborhood or a whole town. Do you think it is possible to change a little bit your approach to include other kinds of cost functions, for example, to take into account the balance of the network so that the batteries are capable of charging when extra energy is available and discharging when needed to balance the local network. Is it possible to think of including your approach into the CityLearn framework and optimize both the charging time, the health of the battery, and the global conditions of the network?
Mm-hmm. Yeah, that's a good question. So expanding the battery size and to use this battery in the higher levels, such as energy storage or power network, I would say AI approach still can be plausible, especially for you if you care about the use of battery. If you want to use a longer battery, the answer is not just to fast charging or higher current. We need to have a better smart strategy to charge the batteries, and that also can be applied to the large scale battery size. And there are more hardware details we need to worry about it. But in the algorithmic side, it also we need to charge the battery and discharge the battery. And the question is, how do we design those charging or discharging profile not violating or not treat the battery worse, right? That's the key to use the battery as long as possible. And that is a key motivation to use this learning-based approach, something figure out that we cannot expect, but still we are guaranteed to supply the power or energy to the demanded side. And so my answer is that yes. And so the key point is, how do we design a profile for discharging charging case from the demanded side and operate it not excessively use the battery like higher temperature, lower temperature, and come up with based on the obtain all the data, then we can design a better solution for battery charging and discharging case in the large scale optimization.